Good afternoon, boys and girls. In this video, we are going to discuss Kirchhoff's rules for circuit analysis. This is going to be our first lesson on electric circuits, so let's first start with the very basics. Let's start with the purpose of why you might build an electric circuit to begin with. The purpose of an electric circuit is to conduct electric current. An electric current is simply the movement of electric charges through an object. For right now, let's just consider these objects to be wires, because that's what you might normally consider when you build an electric circuit. The movement of electric current through a wire or other object, we can measure just by simply taking the amount of charge that flows through a given point and dividing it by the time that we measure that charge to flow through. The symbol for charge, again, is Q, and then the symbol for current is going to be a capital I. And so we can write an equation for current as just the rate of change in charge over time. We would measure electric current in a unit called amperes, which is simply a coulomb of electric charge per second. So if we kind of visualize what's going on inside a wire, our very simple model of electric current is that it's simply positive charges moving through the wire. So if you imagine a river, the current is water moving through the river. For an electric circuit, the current is positive charges moving through a wire. So why do charges move? Well, charges move through wires or any other object for the same reason that any other object would move, and that is to lower their potential energy. So in Physics 1, we've talked a lot about things moving from high gravitational potential energy to a low gravitational potential energy, like things rolling down ramps, for example. Electric charges move because of the same reason. They're moving from an area of high electric energy to an area of low electric energy. So typically, the high and low electric energy sources are the positive and negative ends of a battery. Let's get to that in just a minute. So two things that we need in order to create an electric current. The first thing we need is things for those charges to move through. Conductors are materials that allow charges to move through them very easily. Wires are good examples of conductors. The second thing that we need is a source of electric energy, again, something like a battery. So a very simple circuit might look something like this. You have some sort of source of energy, and then you have some sort of conductive path for those things to move through. You'll notice the third element in the circuit is a resistor, like a light bulb. And what a resistor does is it dissipates the electrical energy as thermal energy. And I think I just realized that I misspelled resistor. Let's try that again. That's better. And so in order for that electrical energy to go away, it's got to be dissipated as some other form. And as we go throughout the next couple of weeks, we'll talk about various ways in order to do that. Okay, so let's talk about some real simple rules for analyzing what's going on inside a circuit. The first is just a statement of conservation of charge. So charge, just like mass, has to be conserved, meaning that in a closed system, the net amount of charge must remain constant. In an electric circuit, what that means is that whatever current goes into a junction must equal the current that leaves the junction, which is a real simple way of saying what goes in has to equal what goes out. Writing that a little bit more fancy, we can say that the net current that goes into a junction equals the net current that goes out of the junction. So let's take this slightly complicated more circuit. You'll notice that there's one battery and that there's 3 light bulbs. And then right here, we have a junction where one wire is joined with 3 wires. So if 8 amperes of current go into that junction, the net current in being 8 amperes, and 7 amperes of current leave through the top and middle wire, 3 up, 4 to the right, and that means 1 amp of current must be going down through the bottom wire rather. If you add up 3 plus 4 plus 1, you would get 8. So the rule is simply at that junction, whatever goes in has to equal what goes out. Now that's got to be true at all the other junctions. So we take this junction over on the right side and then realize that the current in the middle wire is still 4 amperes because there were no other junctions, and the current in the bottom wire is still 1 ampere because there were no other junctions, and the current leaving that junction must be 5 amperes. So it's a real simple rule. Whatever goes in has to equal whatever goes out. That's the first rule for circuit analysis, and again, that's simply referred to as the junction rule. So let's talk a little bit more about this energy aspect. The way that we typically measure energy in electric circuits is with a term that's referred to as electric potential. Because the unit is a volt, electric potential is often referred to as voltage. And electric potential is simply a measure of the potential energy per unit charge. So you can write a real simple equation like V equals U over Q, where U is a symbol for potential energy and Q is a symbol for charge. It's a useful quantity that is independent of the amount of charge. It only depends on the position within the system. So for instance, compare for a moment that train and that bumblebee that are some height h above the ground. Both of those objects having the same height means that we can kind of compare them with each other. Even though they have different energies, they have the same height, and so we could say that they have the same gravitational potential. These two batteries have different amounts of energy because they're different sizes, but they're actually at the same electric potential. So they're kind of like the train and the bumblebee, whereas if we divide the energy by the mass, in the case of the train and the bumblebee, or the charge, in the case of the two batteries, we would get the same quantity. So if you didn't know, the voltage of a common C-cell battery, it's actually written there real tiny on the battery, is 1.5 volts. If you look at your standard AA battery, even though it's smaller, it's still got the same potential of 1.5 volts. And so that's a useful quantity for comparing things that may not necessarily be the same. So in order to move, charges have to move from a location of high electric potential to one of low electric potential. In other words, they roll down an electric hill, to kind of use an analogy. Typically what you do is you create a complete loop from the positive end of a battery to the negative end, which is often referred to as a complete circuit. There are other ways to create an electric potential difference and get a current, but that's typically the most common way. And again, when charges pass through resistors, like light bulbs, they lose electric potential energy to thermal energy. And that's why light bulbs are hot. So let's talk about the second rule for circuit analysis, which is known as Kirchhoff's loop rule. Because energy must be conserved, when any charge in a closed circuit or system returns to its original position, it's got to have the same potential energy at that position. So remember that potential energy only depends on position, not how it got from one point to another. So for an electric circuit, what that means is that the net electric potential change around a closed loop must be equal to 0. Kind of writing that in equation form, that might look like this. Batteries add electric potential energy. Resistors, like light bulbs, remove electric potential energy, and again, they dissipate it as thermal energy. So let's look at an example. Suppose we take a 10-volt battery and we connect it to 4 light bulbs in a circuit like the one I've drawn, or took a picture of actually. Let's suppose that we measure the potential difference across a light bulb, and we get something like negative 4 volts. And then if we draw a loop, like what's highlighted in yellow, we can use those two pieces of information to figure out the voltage V1, I'm just going to call that V1 over here, of that second light bulb, just by realizing that as we go around that yellow highlighted loop, the voltages have to add up to 0. Because if a charge is at this position right here, just put a random X on our circuit, no matter how many times it goes around the loop, it's always got to have that same energy due to its position at that point. So if we take 10 volts and we subtract 4 volts, then V1 has to be 6 volts lost in order for the loop rule to be obeyed and the net voltage change to equal 0. If we do the same thing with the other loop to find that missing voltage, highlight the other loop in red, write an equation, something like that, 10 volts minus 4 volts minus 2 volts minus V2 equals 0, just follow the loop around, then we can solve for that missing voltage and we get something like negative 4 volts. So it's a real simple rule. We can draw a loop around a circuit, any closed loop, the voltage change must be equal to 0. Before we move on, let's discuss some common circuit symbols, because drawing pictures like that is going to be tedious. So those are some common circuit symbols that you might want to make note of in your notebook. A battery is simply one long and one short line, kind of parallel to each other. The positive end of the battery is the longer side. That's just important for us right now for drawing the correct direction of the currents coming from battery. That's going to be more important in later courses that you may take. Wires we can just note with a straight line. Resistors are kind of squiggly straight lines, and then a switch we always draw like this regardless of whether that switch is open or closed. So the circuit that we saw earlier, I can draw using circuit symbols, noting that the positive in the battery is the gold end, kind of sort of like that to represent the battery. The first wire might represent like that. My light bulb I'm going to draw as a resistor, that squiggly line symbol. And then there would be the second wire to kind of close it off. So when we draw circuit diagrams, we're always going to draw those wires at right angles to each other, and then don't ever let them cross if at all possible. In Physics 1, we should never have a situation where we need to draw wires crossing. Because if we draw wires crossing each other, then we're going to confuse that with a junction. And then when drawing the circuit diagram, only the connections and currents and voltage changes are important. The changes, or excuse me, the shapes and the orientations of the wires aren't really that important to us. So where you draw that battery is not important at all. Where you draw the resistor is not important at all. The only thing that you need to show is how current is flowing in your circuit. So those two circuits that I've drawn right there are equivalent to each other. There's no difference for anything that we want to do in Physics 1. Okay, so here's a kind of sloppily drawn circuit diagram that shows 1, 2, 3, 4, 5 resistors connected to a single battery. And the question is, what are the missing currents and electric potential differences in the circuit? So if you want, press the pause button for a minute, draw that in your notes, and try to figure out what the missing currents and electric potential differences are, and then press play and pick it up. Alright, so what I would do is draw a loop, so highlight it in yellow, and then use the loop rule to figure out that first missing potential difference, V1. So I can write an equation like that, 12 volts minus 3 volts minus V1 minus 4 volts equals 0, and then just solve that for V1. So the voltage drop across this resistor right here has to be 5 volts in order to satisfy the loop rule. To find the other missing voltage, I just draw a second loop. I know that the voltages have to add up to 0. Write a second equation. Notice that this time I don't include this one because it's not part of that loop. And so for that second missing voltage, you would get something like a 3 volt voltage drop. To find the missing currents, just realize that there is a junction right there. The current going in has to equal the current going out. So I'm going to call that current through that resistor IB for I bottom. And so 4 amps has to equal 3 amps plus that missing current. So that missing current has to be 1 amp. And then realize that there's another junction on the other side. And so the current coming out has to be 4 amps. 4 amps went in, 4 amps have to come out. All right, so to summarize Kirchhoff's rules, which is really the kind of big takeaway we want from this, simply the current that goes into a junction in an electric circuit has to equal the current going out, and then the net potential difference around a closed loop has to be equal to 0. So right now, depending on where we are in our circuit unit, which varies every year, year to year, this may make total sense, or you may be going, what's a battery? And where we need to close the gaps and really make sure we understand is in the lab. Because in order to understand all this stuff, we have to see it. So at this point, we should be ready to tackle the virtual lab that I created. And then, again, depending on which year it is, right now I think it's 2019, we may or may not have any lab experience to kind of put all this together. So hopefully we have got those two big ideas so that when we see it in the laboratory, it actually makes a little bit of sense. So in 2019, I'll see you in like a week or so. Until then, ta-ta.